I am presenting our work towards calibrating prompt tuning of vision language models. This work focuses on improving the reliability of prompt-tuned CLIP models. Our main goal is not only to improve accuracy, but also to make the model's confidence more trustworthy. Prompt tuning is widely used because it adapts CLIP efficiently without updating the full model. However, most existing methods mainly focus on classification accuracy. In real-world applications, accuracy alone is not enough. A model must also know how confident it should be. If a model gives high confidence to wrong predictions, it becomes risky in areas such as medical imaging, autonomous systems, and safety-critical AI. Therefore, model's predicted confidence should equal to the true likelihood or model predicted accuracy. This will ensure that the model's predicted confidence is calibrated. Post-hoc calibration can adjust confidence after training, but it cannot prevent embedding drift caused during prompt tuning. Our key observation is that prompt tuning creates a dual miscalibration problem. For base classes, the model often becomes underconfident because the logit margins are reduced. For novel classes, the model becomes overconfident because the margins become inflated or unstable. The reliability diagrams and margin analysis show that margin behavior affects base and novel classes differently. Therefore, we need a train time method that controls both logit margins and text embedding geometry, which preserves CLIP geometry by preventing prompt-induced semantic drift and stabilizes class relationships, reducing overconfident wrong predictions, thereby lowering calibration error. To solve this, we propose two complementary losses. First, the mean-variance margin loss stabilizes the logit gap between the ground truth class and the strongest incorrect class. This helps improve confidence separation. Second, the text moment matching loss preserves CLIP's original text embedding geometry by matching the distribution of tuned text embeddings with frozen CLIP embeddings. The total loss combines cross-entropy, margin regularization, and moment matching. Together, they reduce base class underconfidence and novel class overconfidence. Margin loss alone is useful, but it can still create high-confidence wrong predictions, especially on novel classes. This happens because if the model predicts the wrong class, increasing the margin can make that wrong prediction even more confident. Moment matching solves this by preserving semantic geometry. So, margin improves discriminability, while moment matching prevents semantic drift. Their combination gives better calibration, especially for novel classes. We evaluate the method on 11 datasets: ImageNet, Caltech 101, Pets, Cars, Flowers, Food 101, Aircraft, Sun 397, DTD, Eurosat, and UCF 101. We test with major prompt tuning methods such as CoOp, Maple, and Kilogram CoOp, CoCoOp, Proto, ProGrad, and Prompt SRC. The main evaluation metrics are accuracy and expected calibration error, or ECE. Lower ECE means better calibration. For base classes, our method consistently reduces ECE while maintaining or slightly improving accuracy. This shows that margin stabilization is effective for reducing underconfidence. For example, in CoOp and Maple, our method achieves lower average ECE than vanilla prompt tuning in most calibration baselines. The green highlighted values show that our approach gives strong calibration improvement across datasets. For novel classes, the main challenge is overconfidence. The results show that our method reduces ECE while preserving generalization accuracy. This is important because novel classes are unseen during prompt tuning. Compared with post-hoc methods such as temperature scaling and DAC, our train time regularization better prevents semantic drift and gives more reliable confidence estimates. In the loss component study, combining margin loss with moment matching gives the best calibration. The MBLS comparison shows that our margin regularization is more effective because it lifts low margin samples instead of only limiting extreme margins. The distribution shift results also show that our method remains stable under both base and novel class settings. We also test the method on medical modality datasets. This is important because calibration is especially critical in medical AI. A wrong prediction with high confidence can be dangerous. The results show that our method improves calibration in medical settings as well, confirming that the approach is not limited to natural image datasets. Although ECE is the main metric, we also evaluate other calibration metrics. The results on base and novel classes show that our method remains competitive across different calibration measurements. This strengthens the claim that the improvement is not only specific to one metric, but reflects more reliable confidence behavior overall. To conclude, prompt tuning causes two different calibration problems: underconfidence on base classes and overconfidence on novel classes by semantic drift on the clip geometry. Our method addresses both by stabilizing logit margins and preserving clip's text embedding geometry. It is plug and play, requires no architectural change, and adds no extra inference cost. Overall, our method improves calibration without sacrificing accuracy, making prompt-tuned vision language models more reliable for real-world deployment.